Okay, maybe let's get started. Good morning, everyone. Thanks for coming in the summer. I'm delighted to introduce Professor Dr. Kentaro Wada from the University of Tsukuba in Japan. And Ken has made a very special trip to visit us at the UCI. He's taking a detour on the trip to the conference, STDN at Montreal. To share his latest research, actually in the past 8 years already with the whole ITS community. And I think this visit is particularly meaningful because what he will present is actually rooted in the collaboration with us, with me, with Irene, online, with ITS at Irvine, when he was a visiting scholar with us back in 2017. That visit was really productive, and we were really fortunate and honored to have him visit us. And for then and now, and his research on the capacity growth phenomenon, of course, is just one of his research topics. He's been working on some other fundamental contribution in like trade mechanism, like departure time choice, and some many other topics. But today he's going to focus on capacity growth phenomena, and this has gained us significant attention not only among researchers but also among the practitioners. And he will share a lot of cool story with us. And his theoretic framework and the empirical validation work combined with the practical control implementation strategies, I think that represents exactly the kind of research that bridges the gap between theory and the real world applications. And Ken is very wonderful to have you with us today, and I look forward to your presentation. Please join me in welcoming Dr. Kentaro Wada.
Yes, thank you for introduction, Dr. Jin. And hello everyone, I'm Kentaro Wada from University of Tsukuba. And I'm happy to talk here today at ITS Irvine, as mentioned Professor Jin, because about 8 years ago, I stayed at UCI for 1 year. And today's talk is about the progress that follows the theory I developed during the stay. And as I mentioned later, traffic congestion at SAG and tunnel is a topic of great interest in Japan, both academically and practically. And by trying different ways to help practitioners understanding complex our theoretical idea and apply them in practice. Yeah, I have also deepened my own understanding of the theory, and now have begun to see how it can be applied in real-world operation. At the time, 8 years ago, I never thought it could be used in practice, because for me, mainly did the theoretical study about transportation. So both empirical validation and then practical countermeasure were first experience for me. Yeah, but I got some interesting results, so I would like to share them with you today. Okay, let's start. Here's a brief overview of my background. Well, today I focus on the traffic flow theory, but my other main research topics are theoretical study of tradable network permit, which is a kind of market-based transportation demand management scheme, and the dynamic traffic assignment, including route choice DTA and the departure time DTA. Okay. Here is the outline of today's talk, part 1 and part 4. Many stuffs. Okay, part 1 is an overview of June 2018 and what I thought 2020. And part 2 to explain the framework of calibration and validation, then shown the result of multiple sites in Japan and the insight from the implication from them. And the part 3 introduced two driving strategies from the theory that can improve capacity drop. And I will compare these and explain how the result give useful insight for the practice. Okay, and last part, I will present two applications of the theory. One is the design of a new countermeasure based on the theory, and the other is the evaluation of existing congestion countermeasure. So let me explain briefly why sag and tunnel. And there are two main reasons. The first reason is that there are very common bottlenecks in Japan. Because most intercity expressway in Japan pass through the mountainous area, naturally, yeah, this kind, yes. And about 80% traffic congestion occurs having up hills and tunnel entrances. Okay. The second reason is that the long research tradition since from works of Professor Hoshi's group. This includes key findings based on advanced observation, the development of sophisticated simulation, and many empirical results. Yeah, I show some advanced observation. The left-hand side shows the speed recovery profile inside the tunnel, measuring by floating in 1980s. This is not easy even today because inside the tunnel, but they can. And right-hand side show the time-space diagram taken by balloon, not the drone. Yeah. At the moment of breakdown at sag bottlenecks. Yeah. Using this kind of observation, they developed the theory and the simulation. Okay, now let's move on to part one theory. Okay, so what is the capacity drop? So when traffic breaks down, one would logically expect Q discharge flow rate, QDF, is equal to bottleneck capacity. However, in real traffic, the QDF rate decreases by an order of 10%. This phenomenon known as the capacity drop or true capacity phenomena. This phenomenon has been recognized for many years. And the shape of flow density relation with this state typically looks like reverse lambda. This reverse lambda things also pointed by Hoshi in 1983. And there are two possible explanations of capacity drop phenomena. That is, one is a longitudinal sluggish coupling behavior. The other one is a lateral disruptive lane changing behavior. The latter means lane change vehicle in congested flow become moving bottleneck because of bounded acceleration and the reduced discharge flow. However, lane change alone might not explain the capacity drop fully. The former one is more related to sag and tunnel bottlenecks, said that discharge flow decreases because of very slow acceleration or delayed response that lead from queues or traffic oscillation, like this graph. This graph, it takes 2 kilometers for recovering from 20 kilometers to 6 kilometers, very slow acceleration. Okay. And there has been various discussions on the possible cause of sluggish coupling behavior. One common approach to modeling such behavior is to assume state-dependent coupling style. That means the coupling behavior in congested traffic is described using formulation parameters that differ from those in free-flow traffic. However, this approach essentially imposes the capacity drop exogenously. Exogenously, and okay, there is no. And the other possible cause is the variation in acceleration. This means that the capacity drop can be occurred by difference in flow rate between acceleration and deceleration in stop-and-go waves or moving jumps. However, any case, although the bottlenecks likely induce a sluggish behavior, where their connection to capacity drop is not clear. That is our motivation for this theory. The theory introduced here succeeded in describing the relationship capacity drop and bottleneck. And in 2018, identified the minimal factors endogenously explain the capacity drop as sag and tunnel bottlenecks. These are bottleneck effect and bounded acceleration, I will explain later. And Wada et al., Wada and Irina, and Professor Jin completed the description why and how the capacity drop occurred by these two factors. Okay, now move on the modeling part. Yeah, according to Koshi et al., at sag and tunnel section, driver cannot fully compensate for gradient changes or surrounding environmental condition change. As a result, they try to keep their spacing despite unconsciously slowing down. Okay? This bottleneck effect can be described in speed spacing plane like this dot. And the corresponding observation is this one, real observation provided by Koshi. Yeah. And also suppose that the relation can be approximated by piecewise linear curve. We can model the bottleneck effect using a location-dependent spacing speed relation with an increase in the safety time gap. The safety time gap is a reciprocal of this slope.
What is CF again?
Oh, this
Sluggish CS.
car flowing behavior.
Our flow.
Car following behavior. And this is a sluggish car following behavior at sag and tunnel bottlenecks. And let us look at the relation between the spatial change in the traffic capacity and the safety time. Since reciprocal of safety time gap is a y-intercept of flow density plane, an increase in the safety time gap around the bottleneck section, lead to spatial reduction of traffic capacity at this upper figure. Okay, and this is a simple explanation of why the sag tunnel become a bottleneck. This is a bottleneck mechanism at sag tunnel. Now let us illustrate the mechanism of capacity drop, showing how increase in the safety time gap can also serve as a primary factor in capacity drop. That is temporal reduction in traffic capacity, not a spatial reduction. Right? Okay. So this figure shows a time-space diagram of a lead vehicle problem. And according to Newell's simplified coupling model, trajectory of following vehicle is a parallel shift of trajectory proceeding vehicle by safety time gap horizontally and minimum spacing vertical, like this blue figure. However, in sag and tunnel, trajectory become like this due to an increase in the safety time gap inside the bottleneck section. Right? And the headway of this headway is a reciprocal of bottleneck capacity. Okay, the important insight from this trajectory is that increase in safety time gap describes not only local capacity reduction explained in last pages, but also delayed speed adaptation to the lead vehicle in the car frame situation like this. And okay, and furthermore, because of okay, and Also, this vehicle cannot recover the speed instantaneously due to the bounded acceleration. So the next vehicle trajectory become like this, resulting in increase of the headway, which means that the QDF rate is less than the bottleneck capacity already. And a vicious cycle of delayed speed adaptation with the vehicle and bounded acceleration continue like this. Headway further increases. QDF decreases more. And this process continue by stationary state, some stationary state. And here is a traffic state around the bottleneck. I like this animation. This is a traffic state around the bottleneck, free flow, congested traffic, and bounded acceleration. And bounded acceleration state means that driver cannot recognize the head of queue immediately. A kind of sluggish acceleration behavior.
So that bounded acceleration is after people get out of the bottleneck.
Yes.
Get out of the bottleneck.
But for certain tunnel bottlenecks, there is no specific, no clear change of the road condition. So people may not understand that they have passed the bottleneck. This corresponds to the bounded acceleration state. And this video shows the process we explained above using a simulation. And the upper figure is a time-space diagram, and the lower figure cumulative curves. And the left side shows a model with bounded acceleration. This side, no bounded acceleration. And in congestion with capacity drop left-hand side, you can see the Q grows quickly because of the QDL. The slope of cumulative departure curve is reduced. This is a demonstration. Okay. So finally, in the last part of the theory, let us look at the shape of speed recovery profile in capacity drop stationary state. In congestion, the flow in upstream and downstream section are all equal to bottleneck Q discharge flow rate from the bottleneck. And this value is smaller than bottleneck capacity. So it can be shown at this dashed line level. And the same flow rate can be represented in the speed spacing plane by dashed line from the origin like this. And this is a flow rate. And by examining the traffic state at each location, represented by intersection between this dashed line and the fundamental diagram, we can see the speed recovery. The speed recovery inside the bottleneck section. Actually, speed is increases inside the bottleneck section. On the other hand, downstream of the bottleneck, the transition from congested flow to free flow caused by bounded acceleration is observed. This is represented by the inside of the fundamental diagram, and finally reaches the free flow state. And this is a typical shape of speed recovery profile observed in real traffic. The recovery in the recovery in the bounded acceleration state is a driver's isolated acceleration, right? So in this case, the higher speed and the smaller the acceleration, meaning that profile show concave concave and concave here, and approaching free flow speed asymptotically. On the other hand, speed recovery in the congested state, car flowing state, often shows a clearly unnatural convex shape from the viewpoint of isolated bounded acceleration. So this may be the influence the bottleneck appearing in the speed recovery profile.
And that oscillation in the left-hand side of the first graphic.
Yeah,
is
yeah.
always like this, or
And this part is very oscillate because of the stop and go waves upstream of the bottom. Yeah. But this part usually stationary. Yeah, I will show some real data. Okay, this is a concave shape in this convex shape. There are two different states.
So I don't know, I mean, the concave, convex, I mean, in the math terminology, we can say concave down, concave up.
Okay.
I know some people use convex in this.
Yeah,
What do you think?
concave. Yeah. And the discussion on the previous page shows that head of Q, that is the point where the state which from coupling state, the bounded acceleration is the inflection point of speed recovery profile. But many people may think that the start of the speed recovery is at the head of Q, right? But this comes from the implicitly thinking of the bottleneck as a point. However, if we consider the bottleneck as a section, it is more natural to think of the inflection point as a head of Q. This is very important insight from this theory. We will see this by this graph. Yeah, first let us consider case of point bottleneck. In this case, as we can see from the speed recovery profile below, we can see the we can see that the start of speed recovery is indeed the head of Q. But this is such rapid speed recovery is not observed in usual sag and bond tunnel bottlenecks. A typical situation where such a point bottleneck can be seen the congestion caused by accident and traffic signals intersection.
Can I ask what KP means?
Okay.
KP?
Kilopost means a unit. Kilopost means space, position of the load. Yeah.
So in US it's the post miles.
Post miles.
Post miles.
oh.
Yeah, this is the kilo.
Yeah.
Okay.
In Japan. Yeah. I mean, this is not a time. It is a space thing. And if we consider the bottleneck as a section like this, where the traffic capacity decreases continuously, and slow speed recovery can observe inside the bottleneck section. However, this speed recovery goes from directly to flowing to free flow state. It's not realistic in the sense no capacity drop occurs. And finally, this one is a same graph is on the previous page. When a capacity drop occurs, flow rate less than the bottleneck capacity. So state from coupling state, bounded acceleration state inside the fundamental diagram, and a free flow state. With this in mind, it is very natural to think this inflection point as a head of Q. Then this relationship between the bottleneck structure and the capacity of a stationary state becomes very important in the empirical analysis and practical application. Okay, yeah. Take a break. This is a video I took in the congestion caused by accident. in this case, you see that this is the speed. And in this case, the accident vehicle was stopped on the shoulder. There was no lane closure. You can see that these are accident path. And now we have passed the bottleneck section. And it increases very rapidly. This is and within 200 meters, speed goes to 75.
You know what I noticed that was interesting? The acceleration started when there was a light at the end, literal light at the end of the tunnel. There were still vehicles over here, but the traffic, you could see that there was hope. And so everyone started.
Yeah. And this is a speed recovery profile made by self, created from displayed speed and the roadside kilo post. The point, this point is the accident point. And we have a small convex region here, maybe corresponding to the car following speed recovery, but basically the shape of convex shape. Which means
Concave.
concave shape. Concave shape. It's natural. It's interpreted naturally. Isolated acceleration, bounded acceleration. So this means the bottleneck is almost point in this case. However, and the start of speed recovery is indeed ahead of Q, but this is not the case for the second bottlenecks. Now let us move on part 2. The theory explained part 1 has a following model structure. It's simple. That is a position of vehicles at time delta t second later is the current position plus distance travel at a smaller of the two speed. The speed from the fundamental diagram or speed from the bounded acceleration constraint. Right? It's a bounded acceleration version of the numerical component. And the fundamental diagram represents a speed spacing relation with increasing in the safety time gap in the bottleneck section. I explained first part. And the bounded acceleration model represents a natural acceleration behavior in which acceleration becomes smaller as the speed approaches a free flow speed.
Quick question. Sorry, maybe I just don't understand the message. Why is tau indexed by the x or a function of x?
It means depending during the sub in the tunnel section,
Got it.
it increases. So the data validation method as followed. Loop detector data used to measure total discharge flow rate during the congestion, and the probe data is used to measure average speed recovery profile in capacity drop station state. And in the validation, we first check qualitatively whether the convex and concave shape of speed recovery profile actually correspond to the car flowing state or bounded acceleration state predicted in theory. And quantitative validation, we calibrate the model presented earlier and examine the validity of the result. Okay. The target congestion event is here. 2 hour traffic congestion and about 10 kilometers at its maximum Q length. And occurring Komagawa South on the outbound section of Kansai Expressway in Japan. And the loop detector installed to location here is the side of head of the Q. And we analyze data using slanted cumulative curve. The cumulative curve adjusted by subtracting constant slope so that change in flow rate becomes easier to see. And from this figure, we can observe drop in flow from 1,740 to 1,380. Maybe this is a demand level before traffic congestion, and this is a Q discharge flow rate. And from downstream detector, we can observe the drop in flow from 1,570 to 1,380. This is maybe the bottleneck of breakdown flow. And this is a Q discharge flow. And from this figure, we can see the occurrence capacity of it clear. Next, looking at three-dimensional speed surface. This is in this figure, we can see that in the upstream of the bottleneck section, there is a fluctuation of the speed, which shows which state is called affected by stop and go waves. But around the subsection here, this fluctuation almost disappears, and we observe stationary recovery of the speed at all times.
The higher bar is slower.
Higher bar is slower, and And the next figure shows the speed recovery profile of flow vehicle in the stationary congested here state. And each blue line represents the individual vehicle. The left solid line, the space mean speed. And the dashed red line means a plus minus one standard deviation from mean. And from this figure, we can see actually speed profile change from convex to concave. And according to the theory, this part may be the bottleneck section. This corresponding to the downward, steep downward, and gentle downward section.
So
The
the bottleneck is at the end of the downhill.
In this case, maybe relative increase of the gradient minus maybe minus 1.2 and maybe minus 0.8 relatively increase the grade, and this can be sag bottlenecks. This kind. And this figure shows, we want to confirm this state actually the car-flying situation, and this state is actually a bounded acceleration. From loop detector speed data, this position speed of different lane almost same during congestion, which means this is a car-flowing state because due to the constraint of the downstream, there is no room to
Make lane changes.
make lane change, and some vehicle characteristics is observed. On the other hand, this position, there is a speed difference even during the congestion, which means that car-flowing state or congested state is not dominant in this state, which this may be the bounded acceleration state. Then some lane characteristics, maybe in a lane, passing lane, being more aggressive. This kind of characteristics is observed in this state. So our observation from convex to concave, and each part corresponds to the car-flowing bounded state theory intended. So I can conclude that the theory qualitatively well the empirical.
So did you guys check how many lane changes could be there or?
No,
Okay.
no,
But
yeah,
conceptually, kind of unlikely people would make lane changes.
yeah, here. Even, especially for this position, yeah. Okay. So now we move on to the quantitative validation. In the model calibration, we define the bottleneck section based on the speed recovery profile. The starting point of speed recovery is a set of beginning of the bottleneck section. And we set the inflection point in the speed recovery is set as the downstream end of the bottleneck. That is the head of Q. And in step 2, we estimate the fundamental diagram in bottleneck section that is increasing safety time gap for given free flow speed and jump density. From loop detector, we observe the Q discharge flow rate during transition this level. And from probe data, we can obtain the speed of each position. And this speed is this speed can be represented in this this plane or this dashed line. So we can see that this is the current state of this position. And now drawing the congested branch line of the fundamental diagram so that it passes this point, we can estimate the y-intercept and the capacity. This procedure applied to each location within the bottleneck section, we can estimate the time safety time gap and also the capacity of each position. This is a step 2. And in the final step 3, we estimate the parameter of the bounded acceleration, A0. Okay, and head of the Q, the acceleration can be expressed as on the left side here in terms of rate of time gap and flow discharge, Q discharge flow rate and the other factor. And we determine the parameter so that this acceleration matches the acceleration given by the bounded acceleration model of right hand side. And so finally, I explain the overall adjustment. And we can see from procedure, once the bottleneck section is determined in step 1, the parameter in step 2 and 3 are automatically set. So, and from this video, so if we set the bottleneck section, this gray area, then determine the model speed profile. And so we determine the parameter, we finally adjust the bottleneck section so that the model speed profile become close to the observed. And this is a calibration result. Left figure compare the calibrated model with the observed average speed recovery profile. The match in the bottleneck section is almost obvious because since the safety time gap is set accordingly. However, the reproduction of the downstream bounded acceleration state is also good. And the right figure shows the estimated capacity. Yeah, from here to from here, capacity gradually decreases. And this, this capacity is valid because it is close to breakdown flow rate at the beginning of congestion. Even though only data from the capacity drop stationary state are used, but the model can estimate the flow level just before flow breakdown occurs. So we don't use any data before traffic congestion occurs, but we can reasonably estimate the capacity. So we can conclude that the proposed theory is quantitatively valid. And this figure shows application model calibration to other bottlenecks. In all cases, the model successfully reproduced the observed speed recovery profile. And this result demonstrates the robustness of the model in the theory. And the upper part of this figure suggests show the relation between the identified bottleneck section and the vertical curves. From this figure, relationship between the vertical curve and the bottleneck section vary side to side. Example, this part is a downgrade, steep downgrade and a grade. This is a from sag bottom to near crest. And this bottom is this bottleneck only the bottom sag bottom, and this part is downgrade to upgrade. So from this result, the location where countermeasure should be implemented cannot be determined directly from the just vertical curve. We must choose carefully inside. And also the lower part of figure shows the average speed during the 30 minutes just before breakdown. This figure shows the speed reduction tends to occur near the end of the bottleneck section. Speed tend to decrease at this point. And this observation further supported the validity of the calibrated model in capturing both capacity drop flow breakdown, even though it was calibrated to reproduce the capacity drop stationary state.
That's pretty unfortunate, right? That it's not obvious where the bottleneck work will occur. Right, from an engineering perspective, you'd like to be able to.
Yeah, many practitioners think that speed recovery point as a bottleneck,
Right.
then they try to increase this speed. But in my view, or from our theoretical viewpoint, this may be the target.
That is the narrowest point.
Yeah,
In a
yeah.
sense, that's a real bottleneck.
Yeah, real bottleneck. And
But it's not clear that'll work either. That's still. I mean, 'cause you're showing that in that other graph that it kind of could be anywhere on the downslope, the upslope. Even if you change the nature of the where the 2 points are, it's not obvious that either of them will address the problem.
yeah.
So you are looking at the roadway design
Yes.
kind of perspective.
Yeah.
Yeah, I think Mike's coming out. Yeah, indeed, that's kind of unfortunate.
Yeah.
I mean, and no pattern type like a.
Yeah, so there isn't any clear explanation why this happened.
No, currently
So
no.
it's just empirical.
Just empirically show that, varies side to side.
It's not your fault the data says it's not.
But so our theory is important to
Yeah.
identify.
Very.
That is, I mean, for example, the first one is now kind of like the lowest point and it's the end of the thing. But that is.
Okay, let's move on part 3. Okay, control measure for capacity can be broadly classified into 2 types. Those that prevent congestion at bottlenecks, and those that improve the Q discharge flow during the congestion. And the example of HOMA include ramp metering, variable speed limit, and also automatic value technology. And in Irina and Professor Jane in 2020, based on the theory we have so far, they successfully derived the optimal variable speed limit zone. And we focus on this type of strategy. The latter aims to improve sluggish speed recovery behavior through countermeasures such as driver alert via message sign the moving light guide system, I will explain later. And also automated driving technology. And before going into proposed control, let us briefly look at the impact of capacity drop mitigation. If the bottleneck capacity is maintained during a congestion like dashed line, then delay reduce like this. There are two effects here, a decreasing in the queue and a shortened congestion duration. And a rough estimate and some simplification show that if the QDF rate improved by 1%, and if demand capacity ratio is 1.1, a total delay reduced to 20%, average reduced 11%. And these are 5% and 4.5% if the capacity demand ratio is 1.5. Anyway, this small improvement can benefit very large. So according to the mechanism of the theory, we consider two types of capacity mitigation strategy. The first one is the gradient compensation vehicle that improves the sluggish coupling behavior. What happens if vehicle drive with a constant safety term, not increase like this? And here, for fair comparison to the others, its value is equal to the end of the capacity, the bottleneck section, which means the bottleneck capacity does not change. And driving trajectory become like this. From this trajectory, we can see the speed adaptation to the lead vehicle become quicker, right? And then following normal vehicle can leave the bottleneck area like this. This is a first strategy. And the second one is a quick acceleration vehicle that improves sluggish acceleration behavior. Okay, if the vehicle leaves the bottleneck section with a very high acceleration like this, the following normal vehicle may leave the bottleneck area also. However, the effect is valid only if the following vehicle can also take such high acceleration. Otherwise, it becomes a bottleneck. This is the cause of this strategy. So I show some theoretical analysis for this type of strategy. So first, if we consider the situation where gradient compensation vehicle are mixed with normal vehicle, the traffic flow can be regarded the traffic flow with heterogeneous speed spacing with the fundamental diagram. And according to what I told 2020, the macroscopic traffic flow can be approximated by homogeneous model using expected parameter value as an input in this situation. So in the theoretical formulation of these, speed at the head of Q and the Q discharge flow rate, we simply substitute expected value of the parameter, and we can calculate the effect. And the right-hand side figure shows the relation between penetration rate of the GC vehicle and the capacity drop ratio calculated by these formulas.
What's GC?
This is gradient compensation vehicles, no suffered increase in time gap. And okay, on the other hand, the situation where quick acceleration vehicle, QA vehicle, mixed with normal vehicle can be regarded as traffic flow with heterogeneous acceleration bound. As shown also in what I told, such a situation cannot be approximated by the using model using expected value of the parameter. This is because vehicle with poor acceleration performance become moving bottleneck, constraining the following vehicle. So in the numerical experience, we use the parameter that reproduce the congestion at the Kobotoke tunnel in Japan. And the capacity drop ratio in this case is 10%. Yeah, this is the bottleneck capacity and the Q discharge flow rate, and the Q capacity drop ratio is 10%. And the experiment was conducted with big penetration rate from 0% to 100% at 10% interval for each strategy. And for each penetration rate, we conducted 10 random simulation. The specific setting of rate of change of safety time gap and the bounded acceleration parameter for normal vehicle and the gradient compensation vehicle, change of safety time gap is 0. And the quick acceleration vehicle, bounded acceleration parameter is very high. This is the simulation result showing the penetration rate of each vehicle and the capacity drop. We can see that the results are highly contrasting like this. Yeah. Specifically, we can see that the whole gradient compensation vehicle, the increase in the penetration rate and the improvement are almost proportional. On the other hand, QA vehicle, the penetration rate of 90% only leads to 1.3 improvement. So we can say that the improvement of the car following behavior in the bottleneck section is much more important than the bounded acceleration behavior when leaving the bottleneck for the capacity drop, reducing the capacity drop. Okay. So at the end of this control part, we will look at the real-world example related to the theoretical result we have discussed. This is an example of moving light guide system, which has been introduced in several subsections in Japan. This system creates the flow of LED light traveling at constant speed around the car, which stimulates the driver to match the speed of the light. Yeah. And typical improvement of Q discharge flow rate by the system a few percent and to 5%. Not so soon. Yeah. And for optimal space placement of this system, Masumoto et al. Showed that upstream part, this block 1 and block 2 part produce much more improved than the downstream bottleneck block 3 and 4. Yeah. So this, QDF. This result, interestingly, the result is consistent with theoretical conclusion of the QA vehicle and GC vehicle. Okay, this is the last part. Okay. Here I present practical case study where the theoretical consideration so far has been applied in real-life operation. The following case study as a result of activities by a traffic flow theory application group organized by Japan Society of Traffic Engineers. I serve as a representative of this group, which is a joint research team consisting of University of Researcher, 5 major expressway company in Japan, and traffic engineering consultant. The group has been active since 2022 and with aim to bridging theory and practice in traffic flow research and developing a practical solution for expressway traffic management. And in this research group now, we have focused on 2 major topics related to capacity drop phenomena at saddle and tunnel bottom. And the first topic is planning a design of effective congestion countermeasure. This is an idea. Based on the idea of section bottleneck, not the point bottleneck, we can propose a new way to select the countermeasure location. And the model calibration helps accurately estimate the bottleneck section. And as discussion in control part, pinpoint countermeasure near or upstream of the inflection point in the speed of recovery can be especially effective. This is our design concept of new countermeasure. The second is evaluating existing countermeasure and exploring the improvement. The idea is apply model calibration data from before and after implementation by looking at changing the capacity and model parameter. We can understand how the countermeasure works and how to improve it. Yes. This one is a design new countermeasure example. In this case, we first conducted model calibration to identify the bottleneck section like this. This is a bottleneck section estimated from the by the calibration of the model. And that this is a corresponding to also downgrade part of the sum. Yeah. And to improve the covering behavior inside the bottleneck section, we decided to inform the head of queue information by countdown display. We use 4 LED display board. The display shows messages such as end of congestion 300 meter ahead, 200 meter ahead, 400 meter ahead, and go. This is very simple countdown information provision. And compared with the current practice in Japan, such as moving light guide system, which cover from sag bottom to the crest very long, compared to that, this measure is very short and can be implemented at much lower cost. Then here the result. This figure shows a box plot of 5-minute QDF during each congestion event. And these events are before congestion measure implementation. These events show congestion event during implementation, and this event show congestion event after removal of countermeasure due to the facility issue. Yeah. And surprisingly, we found that about 10% improvement in the Q discharge flow rate from 2,600 to 2,900 per vehicle per 2 men per hour. It's very surprising result.
So 10% improvement is almost like no capacity drop.
I didn't check that.
Yeah, for example, if the capacity drop magnitude is 10%.
Yeah.
0.9. Now
Maybe,
0.9,
maybe.
you increase 10%, 0.99.
Yeah.
That's almost no capacity drop.
Yeah.
Is it
I will check. But I think breakdown from 1,500 breakdown flow is reasonable in Japan as a breakdown flow for 1 day. So yeah, maybe.
So that's impressive.
Yeah. Okay. This is the last. Yeah. As an example, evaluating effectiveness of existing countermeasure, I will present a case of Kobotoke Tunnel on Chuo Expressway in Japan. Here, you can see here. The speed recovery information is provided through directional speaker. To encourage a quick recovery speed, the following announcement is made. You have passed ahead of traffic congestion. Please recover your speed as soon as possible. Yeah. But in my view, this is not actual head of queue. This is just the start of speed recovery. Yeah. Japanese engineers tried many different strategies to improve the behavior. And anyway, according to Sato, 7.5 improvement observed in breakdown flow, and the Q discharge flow rate improved by 4%. And They also report that when comparing congestion event with similar demand pattern, the total congestion was reduced by about 40%. And in what I saw 2023, we analyzed the factor why the improvement is observed based on theory. The results show that the improvement in breakdown flow and the Q discharge flow can both be explained by reduction in the safety time gap. I was showing light figure, sorry, very not easy to see. After system was introduced, pink line, and the estimated capacity of the bottleneck section, especially latter part of the section, estimated capacity higher than the before introduction. So due to the increase due to reduction time gap, and this also leads to high Q discharge flow rate. However, the study also pointed out that delay in the speed adaptation worsened and offsetting the benefit of improved acceleration. And this is reflected in the speed recovery profile in lower figure. From this figure, we can see that the red speed after introduction of the system, speed is slower than before. Outside the announcement area, this is announcement area. This is a reduced compared to system introduction. And as I mentioned, this is a start of speed recovery, but we estimate the bottleneck inflection point is here. So this speed reduction may worsen the Q discharge flow rate. So if we can avoid delayed speed recovery in the middle of the tunnel by ensuring the driver correctly recognize the head of Q, a few more percent can be improved in theory. Yeah, this is our Okay. Okay, this is a summary of presentation. In part one, we show the sluggish performance behavior induced by the bottleneck can explain the cause of capacity drop very well. In the part two, we found a clear link between bottlenecks and the capacity drop, enable us to estimate the bottleneck location and the capacity from stationary Q discharge flow rate and the shape of speed recovery. And in part three, we found that the improvement in Q discharge flow varied greatly depending on the location of the countermeasure introduced relative to the bottleneck. And the important message of the last part is that ingenuity of engineer has led to significant improvement in Q discharge flow rate at 7 tunnel bottlenecks in Japan, and deep understanding of capacity through theory presented here will help improve this control system even further. Yeah. Okay, this is a conclude my talk. Thank you very much for your attention. Yeah.
Yeah, thank you very much for the fascinating talk from theory to empirics to practice to control. And they actually talk about the panel. Actually, that was very interesting. You know, when I devised the theory back in when you were visiting, maybe before Ken was visiting, I derived this crazy equation, third order equation, concave up, concave down. And I don't know if this is correct. And it can show me actually there's been observation back in 1980s on the speed profile. Exactly. So that, okay, now I feel comfortable to present my crazy equations. So that was, incredible journey for me as well. Yeah. Then I was very confident that, my crazy equation got to be, okay. So yeah, that, can take it to the next level, as you can see, so many more sides and put it into practice. Yeah. Yes, and especially like the conclusion that, there's a lot of, engineers, there's a lot of, great ideas, great intuitions to improve. And seems that with a good understanding of the theory of the underlying mechanism, we might be further help. I look forward to more of your results. And now let's open up to questions, comments, and I have some questions later for the online for Q&A right now. In the audience, any questions?
Yeah, so I guess I should say, like, one of the main reasons I got into transportation engineering is because of a tunnel sag combination issue in my hometown that I still hate to this day. So I'm wondering, like, you didn't talk too much about tunnels, but you showed us in terms of the sag that it's kind of difficult to pinpoint a priori where the inflection points are going to be. What about in tunnels? Is it the end of the tunnel always? Is it sometimes downstream at the end of the tunnel? What do we typically see with tunnels?
Yeah, typically tunnel section also sag or slope section. So actually we cannot distinguish between sag condition and tunnel condition. Actually, yeah. So in Kobotoke tunnel also maybe due to the steep. Yes.
I didn't know that.
So I always, so this tunnel, I always thought it was a major issue was like, so you kind of go down before you get to the tunnel, then you start going up and you get to the tunnel. But it's not clear to the driver that they're actually driving uphill. And I think that causes some mental cognitive issues in terms of realizing you do need to accelerate, even to keep the space that you want to keep at a given speed. Anyway, that's I'm glad to put the picture more in my head as to what the problem is.
I'm the layperson here, just, would all of this be solved by connected and automated vehicles that don't get distracted? And have a safety gap that's appropriate?
Can resolve capacity drop by automated vehicle, but I concern company strategy is more focusing on the comfortability and safety.
So we'll get concerned that we're zooming past things.
So may become worse than before because company behavior more sluggish, become more sluggish due to such.
We don't trust the car and we
And
would the pace car, I'm thinking of them as a pace car here, would those be an automated vehicle or would those be drivers that are trained to speed up and whatever?
I think pace car can work if designed appropriately. That discussion is related to maybe variable speed limit result of Irina and Perception 2020.
I believe by pacing car, you were talking about the QA, those cars. But I believe for those study, you were using simulation.
That's
not the real. But Victoria said, real world.
Would have to be.
Totally. With the automated cars can serve in those roles. According to those simulation, that's pretty promising.
Right, which people are kind of already talking about, right?
But it's can commonly right now, people for automated car focus more on safety, comfort level, not the efficiency level. This is kind of like a traffic efficiency. This is kind of like a more secondary at this moment, but in the future, there's a lot of possibility. Indeed.
Thank you.
You have a quick question about countermeasure. You mentioned you use the light as a countermeasure for sag. I'm wondering, in terms of tunnel, do you have some kind of countermeasure address the safety time gap?
Similar. This light system also introduced in tunnel.
Light.
And in tunnel there is a speaker for
You should speed up.
emergency situation. So with using such emergency speaker, we can directly inform the intention of the. Yeah, this control system, yeah, implicitly requires people to follow this right, but many people cannot understand what is this. But compared to this, this tunnel announcement more clear to people.
But to be honest, I was really impressed because I don't know how many people would be listening.
Yeah. And,
Especially nowadays with
yeah,
podcasts.
and with the penetration rate of automatic ACC user, this kind of strategy less effective.
But just by using this, you saw a 40% decrease in.
Yeah.
That's really impressive.
Yeah, so this speaker is just asking them to speed up.
Yes,
But you mentioned there's two factors. One is the safety time gap, the other is boundary acceleration.
Yeah.
So in terms of turnout, do we have some countermeasures to maintain the safety time gap to be small?
Yeah, in practice, there is no distinguish between two strategies, but there are two announcement area. Actually, there are two announcement area. Maybe this one for improve the shorten the safety time gap, and this part corresponding to the more rapid acceleration and required acceleration behavior. So in this part, you have passed the head of congestion announcement. This part, you please leave the queue quickly. Announcement is made in this part. Yeah, but in my view, this is not
that effective. Yeah.
Does this, I think you might have said no already, but does the slope of the roadway or the kind of severity of the sag have a direct relationship with the capacity drop, the size of the capacity drop?
Still, I don't know.
Yeah,
Clear relationship. Yeah.
I'm just going back to my kind of roadway design perspective,
Yeah.
right? Like
Yeah.
we can measure the daily congestion cost of one roadway design versus another. That can help us make that.
Right.
But some experts says steep side does not necessarily severe congestion.
Okay.
Yeah, because more gentle side we cannot recognize this is a side.
Right, yeah.
I'm curious, this is probably way out of the scope. Are there cultural differences? Like, do tunnels in Japan travel more efficiently than tunnels in Argentina? I don't know.
Yeah, that's a good question. In terms of capacity drop, I think it has been reported 10% in the United States.
Okay.
In Japan, I don't know about data from other places. Yeah.
But it's from
Like in India, for example, which I think of as a very different place to drive than, say, Japan. I've never driven in Japan, but I assume that Japan.
Totally. I can see the possibilities, but unfortunately not so many high quality research
Right.
on such kind of critical locations.
Yeah.
That would be something, to compare
Yeah.
across countries, across culture. That is a great idea, and I believe many driving behaviors are related to behavior, to the culture. Yeah, that's
Diversity at work, the layperson.
Yeah.
Interesting.
You are coming with your traffic flow theory. Culture dependent.
We have all of your theories and then there's mine, which is.
Yeah. Because this, like in tunnels, happens just because human behavior, right?
Yeah.
So I would say it could-
It's just
Right.
how you visualize that.
Mm.
makes
So it could
people
be
start.
taught,
Yeah,
right?
yeah.
But I think it's a very natural behavior, right? Like when you're trying to.
I think I see a collaboration. Watch out, we're up and coming.
Another PhD.
And, I can share the data.
So you have.
Yeah, I'm just wondering-
moved to online.
How did you come up with these countermeasures?
Yeah, I come up with this idea from accident congestion. Accident congestion, very rapid speed recovery is observed as I shown in the video. So from that, I come up with a countdown.
Countdown,
Wow.
yeah. That seems to be from, of course, I mean, other measures like the moving light guidance and the broadcast, by engineers, a lot of engineering ingenuity. I don't know if they have theory behind it. But many engineers do come up with the way. Basically trying to push people through the bottleneck. You think of pushing people into the subway car, something similar. It reminds me of that. Be faster. That makes sense.
Yeah.
If there's a bottleneck here, let's just try to push people through the bottleneck, right? Different ways. Those are not designed, but this countdown, but so far it was a countdown among all of this. This seems to be most effective, at least tentatively 10%.
Yeah.
Others reports 4%.
Yeah.
And the things.
Comparative, light system and
More studies.
And actually, I come up with by, not me, by engineer, collaborative engineer come up with this design.
But where to place these signs come from the theory. Theory, not coming down in the wrong place, probably does not work as effectively.
Yeah. I want to check such an issue also.
Yeah, that's really cool. Basically, if you count down, get closer to the real bottleneck, then people will become a little bit more aggressive, because in the theory, basically saying that when people getting closer to the bottleneck, people tend to have longer and longer time gap, more cautious in a sense. But if you count down, maybe kind of reverse the effect to let people become more aggressive, so that their time gap does not reduce, then does not lead to the capacity drop and all these effects.
Wouldn't it be almost like in theory that one where you were driving and you were at 30 and 28, 29, and there were still vehicles on the side? I mean, anything that told you that there was something to be worried about was still there, but the people were seeing that a few meters ahead of them it was open, so they changed their behavior, even though there was still the same reason to be careful. Do you remember when you were driving and you were 28, 29, 30, 31, right? It started speeding up, but there were still vehicles on the side.
On the side and ahead, also ahead.
Yeah, but people were looking.
We have some question online. Maybe let's move to June. You're still with us, right? Let me how to unmute June. Okay.
Yeah.
Okay, go ahead. June.
Hello. Yeah. Thanks for the presentations. Do the countermeasures work effectively on the different demand levels? Because I'm especially curious about when demand exceeds the original capacity when demand is too high. Thanks for the presentation.
Which page are you specifically referring to?
Usually the respect of countermeasures.
Countermeasures.
Yeah. So, but I want to know the given input of demand levels of the scenario. Yeah, I mean how the countermeasures work depending on the size of the demand.
Oh, yeah, okay, so maybe the question whether the countermeasure work how effective, whether it depends on the demand level. He wrote down the
Oh,
question in
Okay,
the chat, yeah.
okay.
So,
I think demand level is effectiveness of countermeasure is not depending on the demand level. Because once the condition breakdown occurred and the first job state, there is no effect from the demand level.
yeah, in terms of improving, how much it improves the discharge flow rate, it's
Yeah.
not dependent on demand.
Yeah.
Of course, in terms of total delay, as
Yeah.
you mentioned
Yeah.
that, how it
Demand
will,
level is-
help to improve the delay,
Yes.
depend on demand level.
Yeah.
So
Yes.
does it make sense?
Yes.
Yeah, so June, does it make sense? So basically you think of, arrival curve, departure curve, the countermeasure try to, get larger, larger capacity for the departure curve.
Yeah.
Basically, this part does not depend on demand level, but the total queue length and the delay depend on the demand level. Does it make sense?
Yeah, thank you so much.
Then, do we have any other questions? Maybe Irene, do you have any questions or comments? You're still with us. I know it's a late evening.
I am here. I think it's excellent that you have some empirical data to validate all this theory, and I really like the two strategies. Actually, the first one, I was. It reminds me of some simulation that I ran, I think, while you were visiting, where I was also considering different heterogeneity of vehicles, with different, not only time gaps, but also jam spacing. And I also concluded that the best way would be to eliminate this increased gap with autonomous vehicles, but I don't know how realistic this is if for new cars to know, okay, now I'm in a sack, and even if the humans around me are behaving differently, I should keep my constant gap. But yeah, maybe we can discuss over email or online one day.
Thank you.
It was great to hear you and see you.
Thank you. So regarding the realisticity of gradient compensation automated vehicle, I think with vertical curve information inside the car, yeah, vehicle can adjust their speed, feed forward manner, not feedback manner. Then they can compensate the gradient change smoothly, I think. Yeah. Yeah.
So do we have any other questions or if not, let's thank Ken again for the. So thank you all for coming and also Irene and Jim online.
Thank you.
Thank you.
Yeah.